In our last explainer, we talked about how data applies a kind of force to an AI model, pulling it towards the truth. It's a really powerful way to think about it.
But what happens when that guiding force gets completely overwhelmed? Not by some opposing force, but by just simple, chaotic noise. This is the exact moment that the whole idea of more data is always better starts to fall apart, and it reveals something way more subtle, and frankly, more important.
Okay, so here's how we're going to break this down. First, we'll look at the dilution problem itself. Then we'll compare precision versus fluency to see it in action. After that, we'll peek under the hood at the mechanism of interference, uncover the really weird optimization paradox, and finally, we'll talk about the ultimate limit, the quality ceiling.
All right, let's kick things off with Section 1, the dilution problem. This is really the core idea of how, in the world of AI, more can actually end up being less.
So you have to understand that all training data contains what we call signal. This is the good stuff. It's the real underlying truth, the consistent patterns that we actually want the model to learn.
But on the flip side, pretty much all data also contains noise. Now, noise isn't just flat-out wrong information, it's anything that obscures the signal. So, for example, look at these transcriptions. One person writes, today's weather. Another just uses an ellipsis, right? Neither is really wrong, but that inconsistency creates noise. Same thing in manufacturing. If one person labels a tiny flaw a chip and someone else calls the exact same thing a scratch, the model is getting conflicting instructions. That's noise.
And this brings us to a really key concept, the signal-to-noise ratio. It's just a way of measuring how strong the truth is compared to all the junk. As you keep dumping in more low-quality data, that noise level just keeps rising, and the real signal gets harder and harder for the model to find. It gets diluted.
Which really boils down to this one crucial point. It's not about how much data you throw at a model. The only thing that actually matters is how much signal survives.
So let's actually see this in practice. In Section 2, we're going to explore this difference between precision and fluency with a quick thought experiment.
Let's imagine we have two models. Model A is smaller, and it's trained on this beautifully curated, high-quality data set. Its data has a very high signal-to-noise ratio. Then you have Model B. It's a behemoth, way larger, trained on a massive, totally unfiltered scrape of the internet. So super low signal-to-noise ratio.
Okay, so what happens when we ask both of them the same technical question? Something that has a real, factually correct answer.
Well, Model A, the one trained on clean data, it gives you a short, precise, and factually correct answer. The tone might be a little less confident, because it's programmed to stick only to what it knows for sure. It's bounded by that high-quality signal.
Model B, on the other hand, it gives you this long, super confident, incredibly fluent paragraph, and it sounds so impressive. But when you look closely, you start to see these subtle little inaccuracies, or it might even make up technical-sounding jargon that's completely wrong. It's learned the style of an expert answer from all the noise, but not the actual substance.
And this is where you see the really critical divergence. With Model B, its confidence scores through the roof, but its factual correctness is actually low. The noise in its training data taught it how to sound right, not how to be right.
And the takeaway here is so important, I'm going to say it plainly. Fluency is not signal. Just because something sounds convincing doesn't mean it's correct. So, how does this actually work inside the model? What's the mechanism here? That brings us to Section 3, the mechanism of interference, or how noise basically flattens the model's sense of direction. You know, at its core, a model learns in a really simple loop. It makes a prediction, a loss function calculates how wrong it was, and then it adjusts its internal wirings, its weights, to try and reduce that error next time. And it does this millions, even billions of times.
Now, that adjustment is guided by something called gradients. You can think of every good piece of data as providing a clear directional signal, a gradient, that tells the model, hey, tweak your parameters this way to get a little closer to the truth.
But noisy data, it does the exact opposite. It creates conflicting gradients. Let's go back to that chip versus scratch example. One label is pulling the model's parameters in one direction, while the other label is pulling them in a totally different one for the exact same thing. The model is being told to go left and right at the same time. These signals interfere, they cancel each other out, and they just flatten the overall direction of learning. This interference leads to a really counterintuitive result, which we're going to cover in Section 4, the optimization paradox. Or, put another way, how a model gets better at being wrong. So this brings up the central question of the paradox.
If the model is getting less factually accurate, why do all its internal report cards, like its training loss, keep saying it's getting better? Why does it look like it's learning so well? This visualizes it perfectly. You've got these two curves going in opposite directions. The training loss keeps going down, which means the model is getting really good at predicting the patterns inside its own noisy training data. But at the exact same time, its factual accuracy, how it performs in the real world, is actually declining. It's not learning the true signal, it's just getting an A+ in mastering the noise. And here is why. If you remember one single thing from this entire explainer, please make it this sentence. Optimization does not distinguish truth from frequency.
See, the optimization process is brutally simple. It just tunes the model to get better at predicting whatever patterns it sees most often. So if inconsistent labels, stylistic fluff, and subtle errors are more frequent in the data than the clean underlying signal, then the model will faithfully learn to reproduce that noise. It literally becomes an expert in the errors. And this all leads us to our final section, the ultimate consequence of all this signal dilution, the quality ceiling. This is the unbreakable limit.
Let's just use a super simple analogy. You're making soup. A pinch of salt, that's our clean, high-signal data, perfectly enhances the flavor. It makes everything better.
But if you dump in a whole bucket of salt, our noisy, low-signal data, you completely ruin the soup. It's inedible.
This effect is called saturation. And the most important part of this analogy is this. Once that salt is mixed in, you can't just filter it back out. The model has no idea what's salt and what's broth. The noise has become a fundamental part of what the model thinks soup is supposed to taste like.
So let's put it all together. We know training amplifies whatever is most frequent, and we know that in these huge, unfiltered data sets, noise is often way more frequent than signal. That means that just scaling up more data, more computing power, amplifies both the good and the bad. And if that noise starts to drown out the signal, you will inevitably hit a hard ceiling. It's the signal, not the size of the dataset, that sets the absolute upper limit for how intelligent a model can be.
You cannot scale your way out of a data quality problem. Period. In the end, data quality defines how intelligent a model can ever become.
And this brings our whole three-part journey full circle. First, we saw how geometry defines the map of what an AI can know. Then, we saw how force, through data, defines the pull towards truth on that map. And today, we've seen how value, the quality of the signal, defines the ceiling.
This is why, for any AI system, data isn't just one part of the equation. Data is destiny.